All right, continuing on in chapter 8. The previous video was talking about finding probabilities related to the distribution of a sample mean, or x bar. This lesson is talking about the distribution of a sample proportion, so a different statistic that you can find probabilities related to that statistic. Just like the last one, I'm just starting with a general definition of what a sampling distribution is. Sampling distribution is the probability distribution for all possible values of the statistic that are computed from a sample of size n. The sampling distribution for the sample proportion, to get a little more specific to this lesson, this sampling distribution of the sample proportion p hat is the probability distribution of all values of the random variable p hat. So p hat is really just the variable that's representing the sample proportion. That sample proportion is successes out of the total number of trials or the total number of individuals in the sample. So it's how many times you observed a specific characteristic that you were looking for out of the total number of individuals that you sampled or the total number of trials that were completed in an experiment. So as we go through this, we want to just make sure we understand that definition a little bit better. It feels very repetitive when you're reading it and like they're not really saying anything. But this is what's really happening to produce a sampling distribution. You find a sample of size n. Has to be a simple random sample, or it could be any sampling technique as long as each individual has an equal opportunity to be selected. You compute the sample proportion of individuals with the desired characteristic. So say I'm collecting a sample and I'm looking for the number of individuals who have blood type O negative. So I'd be looking at my total sample size, let's say it's 100, and out of those 100 individuals that I randomly sampled, I want to count up how many of them had the blood type I was looking for. I take how many have that blood type divided by 100 to get my value for p hat. Because it is a proportion of successes, the smallest possible value for p hat would be if I observe 0 people or 0 individuals with the characteristic that I want. So I would have 0 divided by the sample size, giving me a minimum proportion of 0. So the lowest value for p hat is 0. If everyone in the sample had the characteristic I was looking for, that's the other extreme. That would mean that the number of individuals with that characteristic is equal to the sample size. So I would have like n divided by n, which is 1. That tells me that p hat is always a value between 0 and 1. If you're trying to do a problem and you know it's talking about sample proportions and you're trying to find the probability of some number that's greater than 1, you're doing it wrong. A proportion, it's like a probability. It has to be a value between 0 and 1. Otherwise, it doesn't make any sense. So what you would do if you were creating the sampling distribution is you would continue to take samples of that same size over and over and over again. And they have to be unique samples, so you're not including the same individuals in multiple samples. There's no crossover. You get all of these observed sample proportions and you sort of pool them all together to create your probability distribution. Okay, so if sample number 1 had 10 successes, sample number 7 had 10 successes, that shows that I have 2 samples out of, let's say I'm taking 100 samples, that have that probability of 7 out of 100 or whatever it happens to be. But I'm looking at each individual case, I'm counting up how many times the same proportion showed up and making a probability distribution. We want those probability distributions to be normal. If they're not normally distributed or approximately normal, we can't really do any math to help us understand what's happening or make predictions about what could happen. So we do have to assume that there's a normal distribution, or we have to check that there's a normal distribution. But before we get into that officially, to find mean and standard deviation related to p-hat, there are just some simple formulas to figure that out. So this time, instead of x being our random variable, we are interested in that sample proportion, or p-hat. So we would find probabilities related to p-hat instead of x. We need to find the mean for p-hat and the standard deviation for p-hat, so we'll be able to change p-hat values into z values for the standard normal distribution so we can find probabilities. If you have a simple random sample of size n, and that sample is drawn from a population that you can assume is normally distributed, you can find the mean for your p-hat by just finding the population proportion of success. That's typically given to you in the context of the problem. The standard deviation for p-hat is equal to the square root of p times q over n, where p is your probability of success, q is probability of failure, n is the sample size. Just like the last time, when you're looking at that standard deviation formula, as your sample size is getting bigger, that's making the denominator of a fraction larger. Okay, so as that number gets bigger, it's actually making the overall standard deviation smaller. Standard deviation is like error within the sample. We want to decrease the amount of error. So if we get bigger sample sizes, we get better overall results because there's a lower standard deviation. Describing the p-hat distribution, like I said, we want to be able to describe it as a normal distribution. And to be able to do that, if you have a simple random sample of size n that has a population proportion of success of p, which the proportion of success part is missing from this slide, my apologies, the shape of the sampling distribution for p-hat is approximately normal if n times p times q is greater than or equal to 10. You do not care whatsoever what the shape of the original population is. It has absolutely no impact on whether or not you can use the normal distribution for p-hat. You always have to check if n times p times q is greater than or equal to 10. For example, if I know that 76% of Americans believe that the state of moral values in the US is getting worse, and I want to describe the sampling distribution of the sample proportion of Americans who share this belief for a random sample of 60 Americans. I tried to emphasize the word sample every time I said it, because all those times that I said sample is telling us that we're talking about p-hat and not just p or a random variable x. So out of that information, that 76% that's given in the beginning, that is our known population proportion of success. So that's our P. That also tells us that the other 24% of the population would fail or not believe that state of moral values is getting worse. So that Q value is 0.24, and we have a random sample of 60 Americans, so N is 60. I want to check if I multiply N times P times Q, do I get a number greater than or equal to 10? In this case, I get 10.94, which is greater than 10. So I can say that p-hat is normally distributed, and I can say that its mean is equal to the population proportion of 0.76, and its standard deviation is equal to the square root of p times q over n, which is 0.76 times 0.24 divided by 60, and then I take the square root, and I get 0.0551. I do want to mention most of the time the convention is for p-hat. When you're finding mean and standard deviation, you should use 4 decimal values because p is always a value between 0 and 1. You want to keep more decimal places than we did with x bar, simply to make sure that our answers are more accurate because we have a smaller window of possible values for p. With x bar can equal any number that's positive. Actually, x bar can even be negative sometimes, we just don't usually see that. But p-hat has to always be small between 0 and 1, so you want to keep more decimal places. Excuse my cat in the background. if you want to find probabilities related to p-hat. Assuming we're working off the same base problem, for the distribution of Americans who believe the state of moral values in the U.S. is getting worse, find the probability that the sample proportion is at least 70%. So I'm finding a probability for the sample proportion. So probability for p-hat is at least 70%. That means greater than or equal to 70%. I want to interpret 70% as a decimal. Now, from here, I could just go to my StatsMate app, open the normal distribution because I know p-hat is normally distributed. I can put my mean of 0.76, my standard deviation of 0.0551 in the app. I can change it to upper tail for greater than or equal to, and my A value is 0.70, and it'll give me an answer. If I don't have StatsMate, I need to know how to change p-hat to z. Changing p-hat to z is just using the same formula and interpreting it slightly differently. It's statistic minus mean divided by standard deviation, which works out to negative 1.09. That probability I got from a normal table is 0.8621. Interpreting that, I would say that if I got 100 simple random samples of size 60, I would expect about 87 of those samples to have 70% or more individuals who share this belief that was in the premise of the problem. Okay, so more with finding probabilities. According to the National Health Center for Health Statistics, 15% of all Americans have hearing trouble. Suppose a random sample of 120 Americans who regularly listen to music using headphones results in 26 having hearing trouble. What might you conclude? First of all, I know that the population proportion is 0.15. That's the 15% who have hearing trouble. That also tells me that Q, my probability of failure, is 0.85 because P and Q always have to add up to 1. My sample size is 120, so N is 120. It does not give me a proportion directly for my sample. It tells me how many individuals in the sample were observed as having hearing trouble. So I have to calculate p-hat myself by taking x over n, 26 over 120. I rounded this to 0.022. Generally speaking, from what I've seen, rounding your p-hat value to 2 decimal places is okay. It's the mean and standard deviation that you want to keep more, but just watch the directions in the individual problems for how many places you should keep. So I do have to check if n times p times q is greater than or equal to 10 to be able to make any sort of conclusions. And I get 15.3, which is greater than 10. So I can say that p-hat is normally distributed. I should find its mean, which is the 0.15, and its standard deviation, which I plug in p, q, and n in the formula. I got 0.0326. At this point, I can go into StatsMate in the normal distribution, plug in my mean of 0.15, my standard deviation of 0.0326, so I'm ready to move on and think about probabilities. Okay, so this sample proportion that was observed is 0.22. The population proportion that's known is 0.15. So since I want to try to draw a conclusion, I'm looking at the fact that that 0.22 is actually greater than the population proportion. Okay, so I want to look for the probability that p-hat would be greater than the population proportion, or maybe even greater than the 0.22 that I observed. When I find that probability, either in StatsMate or by changing p-hat to z, I got 0.0158, which is an unusual probability because it's less than 0.05. So to interpret that, since the probability shows that it would be unusual to have this observation, this would suggest that the fact that all of my individuals in my sample wear headphones to listen to music, that might be a contributing factor to hearing problems. And more studies should be conducted to test this theory. So that basically covers the lesson. I do have a slide about the steps for solving these problems. I do just want to note quickly, because I only have 30 seconds left, that the changing p-hat to z is not necessary if you have StatsMate. You can skip that step if you have StatsMate. Otherwise, you do have to do this formula and look up the probability using the standard normal table.